Okay, good morning. So today we are going to work, we've been dealing with a lot of different parts of circles, and today we're going to deal with segments in circles. We've been doing arc lengths and sector area, arc measures, angles. So today we're going to try something new, our last topic in circles, which is segments of circles. So let me try and get this writing the right way. And so just a quick review. This looks like something similar you found on the quiz last week. We've got a circle with a segment that's shaded, and the question asks just find the arc length and sector area of this region below. Obviously, arc length we know is just that length right there. We know that arc measure is 60 degrees. We know that because that's what the central angle is. But the arc length is not just the measure, it's how long is it, and that depends on the radius. In this case, we have a radius of 6. So arc length, I know, is going to be basically the way I remember it is it's part of the circumference. The circumference would be all the way around, which is 2 pi r. But I'm just going part way around. I'm going that 60 degrees out of 360. Okay. And by the way, I know r is 6, so I get 1/6. That's 60 over 360 times 2 times pi times 6, and that gives me 2 pi. It doesn't give me units, so I can just say units. And then sector area, I know is just pi r squared would be the whole area, and I just want the shaded part, which again is 60 over 360. So that would give me 1/6 times pi r squared is 36, and that would reduce to 6 pi units squared. So again, a little bit of a review from the last topic on sector area and arc length. Today we are going to talk about segments of a circle, and specifically, another way to think about it is basically the product of a point. So if I look at this circle right here, I can tell these are two segments, right? I've got segment AB, segment DC. And in this case, my point P is actually the center of the circle, which means every one of these segments, so DP, PA, BP, CP, all of these are just radii, which means they're all the same length. So DP times, if I went from DP to PC, that would be the same as AP to BP. So that's pretty straightforward, and so we don't spend a lot of time dealing with segments where they intersect at the center. Okay. Instead, what we want to do, the first topic, and this is our only one for today, is when two segments intersect, but P is not to the center. Okay? So P is not the center, and these two segments still intersect in the circle. So we're trying to come up with some formula that will allow us to say what is DP and PC, what is that product, and what is BP times AP. Okay. So the first thing I'm going to do when I want to talk about this is hopefully build upon things that we've already learned. And in this case, we already know a lot about these arc lengths out here, like this arc length and this arc length, right? And we learned some things with the angles and how that helps with the arc length. So what we're going to do is use what we know about triangles and arc lengths prove something about these segments in a circle. So I drew in these two dotted lines, and hopefully you can see now that we've got two triangles, basically from D to A to P back to A, or sorry, back to D. And I've got from B across dotted line to C, then up to P and back to B. So hopefully you see those two. What's important is that I want you to keep in mind this dotted line from D to A and from B to C. Okay? But if you look at those two triangles, I'm wondering what we could say about those two triangles. And importantly, I want you to look at this arc right here, AC. And note that angle D over here, or point D, if I look at point D, this angle, right, that angle of D, that intersects and makes this arc. But also look at point B and the arc that it makes. And it's the same one. So since both angle D and point B, again, these are inscribed angles, right? So these two are inscribed angles, right? And they create this arc right here. And we know that those angles are half of the arc, but what's more important is that since they create the same arc, these angles must be the same. Those inscribed angles must be the same. So I'm just going to make a little mark here, right here, and right here, to show that angle D is congruent to angle B. Okay? Because they're both inscribed angles and they both create this arc. Okay? Now, you might ask yourself, what are some other angles that show up in both? Well, I've got a vertical angle here at P. Okay. So I know that with those, I can't just say angle P, so I'm going to say, I'm going to label, because there's a bunch of angles at P, so I'm going to say angle DPA is congruent to angle DPC. Okay. So you might think back all the way now, this is past circles, back into triangles, and specifically similarity of triangles. And notice that if I have two angles, I can use my angle-angle similarity theorem. Okay? And in fact, I can then say triangle DPA is similar to triangle BPC. Okay? Again, this is just if you want to stop and just kind of think about it, but we created two triangles. We know angle D and angle B are similar because they both make this inscribed angle here. And then these two angles where point P are vertical angles. So now I've got two similar triangles right here. And with similar triangles, I can make a statement about the sides and their proportionality, right? Similar triangles have proportional sides. So I can say DP over BP, right? First two. That ratio is the same as PA over PC. And that ratio is the same as first and last, DA and BC. DA and BC. Now I want you to look again at these original dotted lines. I know there's a lot going on, but DA and BC. I don't really care about those. I drew those lines in to make the triangles, but DA and BC, I don't really care so much about this. Okay? What I am concerned with are these segments right here. And if I were to cross multiply, I would see that DP times PC. Oops. Wow, that just got really bad. Sorry about that. Times PC equals BP times AP. Okay, and therefore, when we think back over to here, we're wondering what can we say about these segments, and back over here we can say that the product of the segments is equal. So segment times segment equals segment times segment, and this is kind of what you need to know. Another way to think about it would be if I just drew a circle and I made two lines that intersected not at the center and just labeled maybe this P and this Q and this R and this S. Another way to just think about it would just be P times Q equals R times S. That's kind of more of a generic form. Okay, so let's think about it in a couple of examples in the last few minutes. Look, see this example down here. We have a circle. We got one variable. We've got the 4 different kind of segments. So I know from my formula, I know that 2 times 9 equals 6 times x. 18 equals 6x. So x must be 3. That would be one example. And then another example. Again, here they intersect. That's not the center, although even if it was, our formula still holds. But I've got 4 times x. Again, this, looking at this segment in a circle, and this segment where they intersect, I've got this times this is equal to 5 times 8. So we've got 4x equals 40 and x equals 10. And then lastly, one more example down here. Well, that's actually very similar to what we've done before, so I'll just go back up to our first page. So again, we started with this proof. We used both what we know about inscribed angles and the arcs they create, as well as vertical angles to say that we have triangles that are similar, and because of that, we can come up with this formula right here. So hopefully that helps with the homework, and maybe on the homework we'll ask you to create a couple of problems yourself, but that's the first day of circle segments with circles that intersect inside, segments that intersect inside the circle.